You may have noticed when we defined vector spaces that a lot of our examples of vector spaces were actually vector spaces that sit inside of other larger vector spaces. And this is a really common phenomenon, so we're going to give it a name. Whenever we have a subset of a vector space, so a subset S inside of a bigger vector space V, and S itself is a vector space using the operations coming from V, so the vector addition and scalar multiplication coming from V, then we will say that S is a subspace of V. Now, at first this might seem like a very difficult thing to check because there's that big list of vector space axioms, and technically we would need to check that every one of them is true for S. But in fact, there aren't that many we need to check. For S to be a vector space, first of all, it has to be closed under vector addition and scalar multiplication for sure. But it turns out those are actually the only two things we have to check. So if we have a non-empty subset of a vector space, and it's closed under addition, and it's closed under scalar multiplication, then that subset is actually a vector space of V. So really, the only things you have to check are the two closure axioms, which, to be a vector space, of course it has to be closed. But to show that this is true, I mean, all of the algebraic properties for vector addition and for scalar multiplication, since they're true in V, they're going to be true in S, right? Since we're dealing with the same vector addition and scalar multiplication, any equation that's true in V is going to be true in S as well. So if we take two vectors S1 and S2 in S, well, S is in V, so S1 plus S2 is going to be equal to S2 plus S1, right? This is true in V, but these sums are the same in S as they are in V because the vector sum is the same. And so this equation is also true in S. So, all of the algebraic properties, commutativity, associativity of addition and scalar multiplication, and distribution, all of those we get for free. The things we need to check are closure, which actually we don't need to check because we're assuming, and we need to check the existence of an additive identity, and we need to check that additive inverses exist. So let's suppose that we have some vector inside of our subset S. Well then, the scalar product -1 times little s is in capital S, right? That's because we're assuming that capital S is closed under scalar multiplication. But then S plus -1 times S is 0. And this is in V, right? Because something that we've proved before, or maybe I've asked you to prove, is that this -1 times S is actually the additive inverse of S. So that's what we would call minus S. So when we add S and minus S, we get 0 in V. But, minus S is in capital S. That's the scalar multiplication closure. But then now S and minus S are both in capital S, and so their sum also has to be in capital S. That's closure, the assumption that we made about closure under vector addition. And so that means 0 has to be in S. So 0 is in S. Also, for every S in S, negative S is in S. Again, that's a scalar multiplication closure. So we do have a 0 vector in S, and we have additive inverses in S. So those are really the only extra vector space axioms that we explicitly need to check, and you can see here we've checked them. So this proves that for a subset inside a vector space, if you can show these two closure properties, then your subset really is a subspace of V. Of course, if you have a subspace of V, it does satisfy these two closure properties. So what we're saying is for subsets of a vector space, being closed under these two operations is equivalent to being a subspace. So, saying a subspace is a vector space kind of makes you think, uh-oh, there's going to be a lot to check. But no, there are actually just these two things to check. So let's look at some examples of subspaces. I guess some examples other than ones we've already looked at. So let's, just as an example, let's check that this is a subspace in R3. So the set of all vectors that looks like A plus B, B, and 2A minus B sitting inside, or for A and B, real numbers. So remember, all we have to check is that it's closed under addition and closed under scalar multiplication. So first let's check that it's closed under addition. Well, to check that it's closed under addition, we have to take two vectors in this collection. So here's one, A plus B, B, 2A minus B. There's one vector in that collection. And then add another vector in this collection. Now, the constants are going to be different, so we can't write A and B again. We have to use different symbols. C plus D, D, and then 2C minus D. So, the names of these variables isn't important. What's important is the pattern they make in how they show up in this vector. And the pattern is the same here as it is here, so both of these vectors are in this collection. So, now let's add these together and see if they are again in this collection, in this subset. So how do we add these? Well, remember, when you're talking about a subset or a subspace, the vector operation, the sum and scalar multiplication, are the vector operations from the larger ambient vector space. So this vector sum is the usual vector sum for R3. So to add these, we just add entry by entry. So A plus B plus C plus D, and then B plus D, and then 2A minus B plus 2C minus D. Okay, now we have to ask ourselves, is this resulting vector sum in the set that we were working with? Well, it's kind of hard to tell at first glance, but remember, what we really need to check is it possible to come up with real numbers that make this pattern? So we need to write this pattern. Okay, well, it's easy to identify what should be in this spot because that's just going to be this entry down here. So B plus D is playing the role for our sum vector that B did originally up here. So that means right here we should have B plus D. So we can rearrange this to make that happen if we put A plus C over here. Okay, so now A plus C in our sum vector is playing the role of A in the original. So that means hopefully we should have 2 times A plus C minus B plus D. Is that really what we had? Well, here's 2A and 2C, so that's 2A plus C. And here's minus B minus D, so that's minus BD. And so this sum vector does have the form that we wanted. So this is in our collection. I guess let me name this S. So this vector is in our subset S. All right, so now let's check the scalar multiplication closure properties. So again, take a vector in S, A plus B, B, 2A minus B, multiply it by a scalar, and see if it's still in S. So when we multiply this by a scalar, this is RA plus RB, and then RB, and then 2 times RA minus RB. And I've multiplied things out and grouped things in this way, specifically so that we can tell that yes, this still is in S, right? We have a real number here that is also there, and we have a real number here, R times B, that is also here and here. So I forgot my closing parenthesis here. Right, so it follows this pattern. It is of this form, so that means it's in S. So this subset of R3 is closed under vector addition, also scalar multiplication, and that means that S is a vector space. All right, so fair enough. Let's look at another example. Let's check if this collection is a vector space. So I said verify that it's not, so it turns out it isn't. But how could we check that? Well, there are a few things that we could check. Of course, we could just, well, I guess one thing that we don't need to check is, does it satisfy, or do the vector operations in this subset satisfy all the algebraic properties that they need to? We don't need to check that because obviously the vector operations do satisfy all of those algebraic properties because the vector operations are inherited from R2. So the things that we might check to see if to verify that this is not a subspace, we might check if it's closed. We might hope to come up with an example showing that this isn't closed under vector addition. We might come up with an example that shows this is not closed under scalar multiplication, or we might come up with we might demonstrate that zero is not the zero vector is not in this subset. That would also demonstrate that this is not a subspace. For this example, as with I think all examples, we'll be able to do any one of those. So just as an example, 1 minus 3 is clearly in this subset. So let's add that to itself. Right, so let's call this one capital T maybe. So this one is clearly an element of capital T. This one is the same element of capital T. So if we add them together, do we get another element of capital T? So the vector we get is 2 comma minus 6. So now we have to ask ourselves, is this in capital T? Well, capital T is made up of all of the vectors that look like this. So is it possible to write 2 comma minus 6? Is it possible to write that as 1 minus a and minus 3 plus 2a? Well, if so, a is going to have to be minus 1 in order to make this first entry equal to 2. So we're going to have a equals minus 1. But if a is minus 1, this second entry is minus 5 and not minus 6. So, right, this can't happen. It's impossible to choose a to make this equal to the vector that we got, 2 comma minus 6. So the answer here is no. 2 comma minus 6 is not in T. And so T is not closed under vector addition. And so T is not a subspace. Okay. Now, by a similar token, you can check that the scalar product 2 times 1 minus 3 is not in T. Right? So here's a scalar product that is not in T. Of course, this scalar product is that same vector. Also, it's a good exercise, if you don't see why this is the case, it's a good exercise to show that actually the zero vector is not in T. And so, this subset T doesn't contain the zero vector, so it can't be a subspace. All right, so there's an example of what a not subspace looks like. Of course, we could have subspaces in any larger ambient space. It doesn't have to be Rn for some value of n. So for example, consider the inside of the matrix, the n by n matrices. Consider all of the matrices whose sum of diagonal entries is equal to 0. So this, if you have a square matrix n by n, then if you add up its diagonal entries, that's called the trace of the matrix, which is written TR of A, like this. So what I'm saying here is that this time our subset is the collection of matrices A, where A trace of A is 0. And of course A is in n by n matrices. Okay, so let's check. Let's check if this is closed under vector addition and scalar multiplication. So we have to take two matrices in this set, in S. And if it's in S, then let me write it this way. So we're going to take two matrices, A and B, in our subset S. Then we know that trace of A is 0, and we know that trace of B is 0, right? Because that's what it means to be in S. Your trace has to be 0. So what is the trace of A plus B? Well, let's write out what A plus B actually is. So A plus B is the matrix, right? In this first entry here, it's the 1, 1 entry of A plus the 1, 1 entry of B, right? And so on down the diagonal, down to this bottom right corner, it's the NN entry of A plus the NN entry of B, right? That's how you add matrices. You just do it entry by entry. Of course, there are a lot of off-diagonal entries as well, but since we're going to add up the diagonal entries, we really only care about the diagonal entries. So what is the trace of this matrix? Well, this is the sum from 1 to n of AII plus BII, right? So I'm saving myself some work by using sum notation instead of writing out this big sum. But this is, we can rearrange this sum. This is the sum from I equals 1 to n of AII plus the sum from 1 to n of BII. Right? This is just rearranging this sum. Since real number addition is associative and commutative, we can rearrange this to look like this. Now this first piece here, that's actually just the trace of A. That's the sum of the diagonal entries of A. And the second piece is the sum of the diagonal entries of B, so that's the trace of B. But remember, we said the trace of A was 0, and the trace of B is also 0, and so this whole thing is 0. So the trace of A plus B is indeed 0. So A plus B is in our subset of matrices that have 0 trace. All right. Also, we need to check what about a real scalar times A. So what is the trace of R times A? Well, what is R times A? It's R times the A11 entry, and then so on, down to R times the ANN entry, and a bunch of off-diagonal entries, but again, we only care about the diagonal ones since we're about to compute the trace of this matrix. So the trace of this matrix is the sum from I equals 1 to n of R times AII, but right, we can move this R outside. That's essentially factoring out the R. So we have R times the sum from I equals 1 to n of AII, and this is R times the trace of A, but the trace of A is 0. So we have R times 0, that's 0. So now we know that any scalar times an element of S is in S. So that means S is closed under vector addition and scalar multiplication. So S is definitely a subspace of M and N. It's called the subspace of trace-free matrices, which turns out to be an important subspace in applications.